All right, we are on to applying what we learned with the first derivative and the second derivative to model an optimization problem. So optimization is just finding the maximum or minimum, but in a real-world context. Okay, so we're talking story problems. That's what we're going to be modeling with some mathematics. And to solve an optimization problem, either with the calculator or not calculator, using either the first or second derivative test for extrema. All right, so guidelines for solving optimization problems. I got too many things on this slide. Okay, well, 1, identify the given quantities and the quantities to be determined. Draw a sketch if applicable. So this is just kind of how you've always been taught to start a word problem in math class. Write a primary equation for the quantity to be maximized or minimized. This will be the one that gets the calculus. Okay, so we'll be taking the first derivative of this and using a first derivative test. Reduce the primary equation to be expressed as a function of one independent variable. So we might have another equation that we'll sometimes call the helper equation that will help us get our primary equation into a single variable so we can take the derivative with respect to that variable. Determine the feasible domain. This will just be basically thinking about what's a reasonable answer for the real world situation that you're solving. Determine the maximum and minimum values using the calculus techniques learned previously. Make sure your answer is within what would be reasonable. So the good news is for the next 2 days, 3 days that we're working with optimization, there is no new calculus. However, we are going to be applying the calculus that we've learned, so we need to make sure we really have a good understanding of that. Okay, so express the number 100 as the sum of two positive numbers whose product is as large as possible. So when I read this, I'm going to take two positive numbers. I will call them x and I will call one y. And I want to make their product p. Well, product would mean multiplication. I want to make their product, and keep this in green, as big as possible. So this is the thing that I would like to maximize, knowing that the sum of those two positive numbers is equal to 100. So the maximize equation is my primary. In this case happens to be a product. This one will be what I'm going to refer to as my helper. It will help me to solve this problem. So right now, my product, I've got my primary equation. I need to now reduce that primary equation to be expressed in one variable. So I can choose to make that product in terms of just x or in terms of just y. I'm going to choose to use my helper and say that y is equal to 100 minus x. So now my primary equation, the one I would like to maximize, is in terms of one variable, just x, right? One independent variable. So now if I want to find the maximum of something, I'm going to take the derivative, p prime. I'm going to set that derivative equal to 0. And I get x equals 50. So now there's two options to figure out if 50 was a minimum or a maximum. One option is to take the second derivative. P double prime is going to be equal to -2, which means that P double prime of that critical number, 50, is less than 0, which means my graph was concave down and x equals 50 would be a relative maximum. The other thing I could do is I could set up a number line for p prime. Thinking about my domain, if I have two positive numbers that add up to 100, technically I shouldn't be equal to 0. I'm going to be looking between 0 and 100. 50 was my critical number. I can do a number line test. If I pick a number like 25, 100 minus 2 times 25 is positive. 100 minus 2 times 75 would be negative. So again, I have a maximum at x equals 50. In this case, I think the second derivative test for extrema is easier, right? Find the critical number, figure out, was your graph smiling or frowning in that critical number? So the question said, express the number 100 as the sum of two numbers. Well, we know that at x equals 50, we have a relative max. And if x equals 50, I'm going to go back to my helper equation. My helper helps me get started and helps me to end. My y is also going to be 50. So at x equals 50, there's a relative max, which means that y equals 50. And my sum of my two numbers, the way the question is worded, would be 50 plus 50 equals 100. So again, no new calculus there, just had to set up my primary equation, which was in green, use my helper to get started, and use the helper to get done. All right, example 2 of 3. A rectangular plot of land is to be fenced in with 12,000 feet of fencing. You must use all of the fencing and also have a rectangle with maximum area. What are the dimensions of the plot of land? Well, it says that we are supposed to have a perimeter of 12,000 feet of fencing, right? And we're looking to maximize the area. I'm going to draw a picture. I will call this side X, which means this side is X. This side would be Y, and this side would be Y. And I'm trying to maximize the area. So the area would be X times Y. This is what I would like to maximize. And I know that X plus Y is equal to my 12,000 feet of fencing. So 2X plus 2Y equals 12,000. My answer is supposed to be written as the dimensions of the plot of land. Well, I have my primary and I have my helper. I'm going to use my helper to get started. I'm going to, again, just solve for one of my variables. So 2y would be equal to 12,000 minus 2x, which means that y would be equal to 6,000 minus x. That 2 would go away. So my area that I'm trying to maximize is the same thing as x times 6,000 minus x. I now have my primary equation into one independent variable. So I can use calculus techniques. A prime is going to be 6,000. I'll switch my colors. Minus 2x. I'm going to set that equal to 0 and also consider where that would be undefined. I should have mentioned that in the first one. But because this is just a linear function, we won't ever be undefined. X is going to be equal to 3,000. And again, I could do a number line, and I could think of my reasonable fencing, right? 0 to 6,000, because I have to have two sides. So it would be a situation of fencing being completely right next to each other, making two lines rather than a rectangle. Or I can find my second derivative, a double prime, would be equal to -2, which means a double prime at that critical number of 3,000 ends up being -2, so less than 0, which means my graph was concave down, which means at that moment I have a maximum. So we have a max at x equals 3,000. I'm going to use my helper to figure out what my y value should be, because it said I needed to find the full dimensions of this field, or this plot of land rather. So my y value is also 3,000. So my dimensions will be a 3,000, was this feet? Yes, 3,000 feet by 3,000 feet for my plot of land. Now, if you're saying, well, Ms. Schwartz, that happened in the first problem, it's coming out the same, right? 50 by 50, 3,000 by 3,000. I do agree with you, because the square is the rectangle with the largest area. And so that's all well and good, but tonight for homework, you're going to have a problem that looks like this, where you have x and y for your perimeter of your fencing, but you're going to build your plot of land along a river where you don't need that third or that fourth side. So that's going to change what your dimensions are going to be. Okay, so we can use calculus to justify finding where the maximum happens. Great. Making sure I answered the question. Sometimes the question asks you to also find the area, but it doesn't in this case. It just asks us to find the dimensions. All right. We're going to step it up a little bit. You are designing a soft drink container that has the shape of a right circular cylinder. The container is supposed to hold 12 fluid ounces. 1 fluid ounce is approximately 1.80469 cubic inches. Find the dimensions that will use a minimum amount of construction material. So the thing I would like to minimize is going to be the surface area. Because what is this can made out of? It's made out of aluminum. I want to use the least amount of aluminum possible. So the surface area is going to be the thing I would like to minimize. The surface area of a right circular cylinder from geometry, we're going to have a circle for the top, pi r squared. We're going to have a circle for the bottom, pi r squared. And then if I were to cut this Sprite label and unwrap it, some of you might remember we have h, and then this we have is the circumference of that circle. So I have one Sprite label, 2 pi r h. So my total surface area is going to be 2 pi r squared plus 2 pi r h. So what can I use to be a helper equation? Well, my volume is supposed to be 12 fluid ounces. So the volume will be equal to pi r squared h, another formula from geometry. 12 fluid ounces is what this is supposed to be equal to, but all of this stuff was in cubic inches. So 1 fluid ounce is approximately 1.80469 cubic inches. So 12 ounces, I'm just going to do a little unit conversion, 1.080469. So just thinking about chemistry, right? If I have 1.80469 inches cubed per 1 ounce, I'm going to multiply that by 12 ounces, factor label. I end up with my volume. I'm going to grab a calculator nearby. Hopefully you have one too. 12 times 1.80469 equals 21.65628 is equal to pi r squared h. So the next trick becomes figuring out how do I get my surface area equation. Right now it has r's and h's. That's too many. How can I use my helper to solve for one of those variables? Well, I think it's easiest to solve for h because otherwise I'd have to take square roots and such. So my h, I'm going to divide by pi, and I'm going to get 6.893. We're going to always use 3 decimal places for AP Calculus. Divided by r squared is equal to h. So I can go to my surface area equation, and I now have 2 pi r squared plus 2 pi r times 6.893 over r squared. Okay, I'm going to leave you to clean this up, find surface area prime, and find me a critical number, r. So you're going to take the derivative. You're going to set the derivative equal to 0 and consider where it may be undefined, and then come back and meet me. Pause now. All right, let's talk it out. So I'm going to clean this up. 2 pi times 6 gets me this 43. R over r squared is just r. Rewrite that as r to the negative first to make my taking the derivative easier. Here's all of my derivative work. I have a critical number when my derivative is undefined, so r equals 0. But also makes sense because the radius of a can won't be negative. Going through and solving, I've shown all of my steps. Please be really careful that you put parentheses around your 4 pi when you divide in your calculator. Otherwise, you're going to get the wrong answer. You need 43 divided by the quantity 4 pi. Not divide by 4, then divide by pi. That causes chaos. Taking a cubed root is under the math portion of your calculator, or you could raise it to the 1/3 power. In this case, it makes sense to use surface area prime rather than the second derivative. Then I use my helper to find the h. We will talk about this one in class when you return.